It's a pleasure to have Gye-Seon from Seoul National University, and he will be speaking about convex real projective structures on reflection orbifolds. Gye-Seon, over to you.
Thank you. Thank you, organizer, for inviting me this nice conference. In fact, this is first time in India. I really enjoy it a lot. So today, I want to talk about the convex real projective structure on a reflection orbifolds. But I try to start with some motivations. So, if you want to understand, for example, the Teichmüller space for the closed surface, and to want to parameterize this Teichmüller space, there are a bunch of ways to parameterize, but one way you can decompose this closed surface to the pair of pens. Okay, then you first parameterize the space of hyperbolic structure on a pair of pens. Okay, then you do the gluing. Okay. Then you can actually parameterize this whole space. So the key point is that here the building block for the two-dimensional case is a pair of pens. You know the pair of pens, you know everything, okay? But here, okay, later I'll explain a bit more, but if you try to parameterize some convex project structure on some manifolds, but there are, let's say, for example, 3 manifolds, okay, closed 3 manifolds. There are too many 3 manifolds. There is no one building block you can actually try to use, okay? So it's hard. So what I want to do is that I specifically use some particular family of these orbifolds, which I call the reflection orbifolds. I will describe using some polytope. It's more easy. Then I think we can actually try to understand such the orbifold, which we can actually decompose in some building block, which will be some simplex. Okay, and then simplex, okay, is most easy, probably the polytope, right? Then I think you can understand gluing and then everything. Okay. Okay, so let's start with dimension 2. Okay, so I draw this is a projective model of a hyperbolic space, a hyperbolic plane. Okay. And then here you see this is the polygon. Okay. And then I specify the angle. Okay. Here this dihedral angle is a pi over L1 and etc. Okay. So I want to parameterize the space of the polygon and the hyperbolic polygon with these angles. Okay. So how we can do this? Probably I think it's basically baby case of this like a surface case, right? This is a polygon. So let's start with this simple example. Okay. So here I just write 2. In fact, it should be the pi over 2. Okay. And then pi over 2 and pi over 5, but it's fair to just write the number. Okay, much easier without pi. Okay. So then to parameterize this guy, I look at the 2 triangles, okay? So the one is this one and the other one, 2 triangles, okay? So here you can see these vertices, ideal vertices, okay? So this is, and then this is ideal vertices. So you start with this 2 triangle. Basically, I want to use these 2 triangles to have this guy, okay? So what can we do? So you can deform it, okay? So the triangles, at the beginning, the vertex was this vertex and that vertex, it was ideal vertex. But now this vertex is outside of this hyperbolic plane. So it's a hyperideal vertex. Okay. Then what you can do, you can actually, here, this line, this is geodesic, okay, is basically the Lorentzian orthogonal to this vector or the vertex. Okay. Because here I use a Klein model once again. Okay. Then if you truncate the vertex, then what happens is that here the angle is right angles. Okay. Then when the length are the same, then you can actually glue. right? Okay. So in this way, to understand this, the space of this polygon with a fixed dihedral angles, we can use basically the two triangles, but I mean the space of the hyperbolic triangle you can easily understand, and then basically using here, of course, in a surface case there are these twists, but in this case it's a polygon, there's no twist. Simply whenever this the length of the edge is matched up, you can glue. That's it. Okay. So in fact, so this is a way to understand this polygon, okay? Hyperbolic polygon. So, but this is really the key idea. Okay. So that's how I wanted to. Are there questions? Okay. That's right. So, yeah, that's right. So here, I try to understand this guy, and then this guy, whenever the lengths match up, and then I glue. So, yeah. Okay. So, but then, so this is the hyperbolic setting and easy to understand. But I think I actually give the motivations here, trying to use a triangle to understand the general polygons. So this is the key idea. Okay. For my story, I think is the reflection group is basically such an object. You can also construct the reflection group. So this polygon, especially the dihedral angle is pi over something, right? Okay. So you can consider the reflections along this edge. Okay. So there are, for example, in this case, 5 reflections, right? So you can construct a reflection group. So for the reflection group, we need this abstract group, which is a Cox group. So I think I need to introduce what is the Cox group. Okay, so first of all, the Cox matrix is simply a symmetric matrix, okay, where the entry is 1, 2, it can be also infinity. The diagonal entry is 1, and then off diagonal 1 is different from 1. Okay, so it can be 2 or the infinities. Okay, so this is a Cox matrix, and whenever you have a Cox matrix, you can simply build a group which is called the Cox group. Here, the generating set is the S, this finite set S, and then the relation is very simple. So ST, and then you put this number MST. So for example, the S and T is the same, then MST is 1, right? So I mean every generator is involutions. Okay. Okay. So this is this generator, and this is relations. So we have this matrix. This is group. So we call the Cox group, and we can encode this information of the Cox group using a diagram, and then we will use quite time to time. So how we can construct a diagram? First of all, the node of the set of nodes of this diagram is S. Okay. So we have the S node or the S vertices, and then the 2 nodes are connected if this MST, I mean this number is not equal to 2. So the 3, 4, and infinities. And then we put the labels on this edge, simply this number MST. Okay, so I give you the examples. Also, quite often we omit the label of the edge when the MST is 3. Okay, whenever you see the 3, I just omit it. Okay, so this is the Cox matrix. So you see all the diagonal is 1, and then the off diagonal is 3. Here I put the 3 and 2. So from this Cox matrix, okay, we can build a group. So how many generators? So we have 4 generators, so S1 to S4, and then every generator is involutions, right? Then, for example, here, so S1 and S2. So this is the 1, 2 entry, right? So this is 3. So I put here the 3, right? Okay, so then for the diagram here, so 1, 2, so is a 3. So it should be connected. These two vertices should be connected, and then I should put the label 3 here. But as I said, we just omit the label 3. So it's and then 1 and 3. The 1, 3, and 3 is a 2. So 2, I think I said that there's no edge between them. Okay, there is no edge. Okay, so this is just one way to describe this special group, which is Cox group. Okay, that's it. Okay, then the Cox group is people call irreducibles when the graph is a 0. That's right. So the 2, when the MST is 2, then there is no edge. Okay. Sorry. So there is edge connected when MST is different from 2. Okay. Yeah. Thank you. Yeah. Okay. So the graph, this Cox diagram is connected, is topologically. Then this is we call the group is irreducible. Okay. Then it's a well-known theorems by the Wimberg and Magulus. Then every irreducible Cox group, spherical, affine, or right. So spherical means, in fact, the Cox group is a finite Cox group. The group is finite. Okay. And affine means the Cox group, this group is virtually abelian. Meaning there exists a finite index subgroup, which is abelian. Okay. So in some sense, the spherical and affine case is is simple, right? Finite group or the abelian group virtually. And then the other case is all the large, means it has a finite index subgroup, which subject to the free, non-abelian free group. Okay. The name, actually, the Cox group is coming from the fact that the Cox classified is the spherical and affine Cox group. Okay. So as you can guess, we are interested in the large Cox group. Okay. Because the other two cases, there is classifications, also it's easy. Okay, so at the beginning, for the motivation, I talk about this hyperbolic polygons, so hyperbolic reflections. But I want to enlarge my geometry, because Sarah mentioned this geometric structures. So especially, I'm interested in the projective geometry, the real projective geometries. Okay, so here my V is simply the D plus 1 dimensional real vector space. Okay, then you consider the projective spheres. So this is simply the space of half line starting from the origin. Okay, so it's simply the double cover of the projective space. And the space, the group of projective orthomorphisms of these projective spheres is simply the SL plus minus B, which is the matrix group whose determinant is plus minus 1. Okay, so this is again the double cover of this PGL D plus 1R. So now I define the reflections. So this is the generalization of the hyperbolic reflections. Okay, so here the reflections, projective reflections, is simply the involutions. Okay, which fix the projective hyperplane. So involutions can fix, of course, the raw dimensional, the subspace. But when I say reflections, it should fix the hyperplanes. Okay, co-dimension 1, right? Point-wise. Then, of course, we can write it, this reflection, the sigma is simply the identity minus the alpha tensor B, where the B is vectors and alpha is a linear form or the linear functionals. Okay, so simply with this alpha B is 2. So in other words, the sigma v, so here the v is any vectors, and then the v minus alpha v, this is number, right? And then the b. Then you can easily see that the vector in the corner of alpha, okay, then is a fixed point, right? And then if you put the b, then this become a b minus the 2 times b, right? So it's minus b. It's really the vector is b changed, sent to the minus b. Okay. So this is the reflections. Okay. Then, so I'm interested in some convex set in a projective sphere or the projective space. So when I said the C is convex, if there exists a convex cone in this vector space V, such that the projectization of this convex cone is C. Okay. So you can imagine what should be convex. And then the properly convex, if it is convex, and the closure is some affine chart. So the affine chart is, if you imagine a projective sphere, and then one-dimensional roller sphere. If you remove it, then there are 2 components. The one of the components, either way, is we call affine chart. It's basically the R to the D, right? Inside there is closures. The closure is lying in this affine chart, and then we call the properly convex. Okay. So then the polytope is simply the properly convex set with the non-empty interiors, such that we can describe this polytope as intersections of the half space. Okay. So here, I mean, this is simply so this alpha I is the linear functioners, right? So the linear functioner alpha I x is less than 0, so some half space, right? And then I take the intersection, so intersection of the half space, some cone, right? And then I take the projectizations. Okay, so that is my polytope, projective polytope. And okay, so I should also mention, whenever I say the face set, then this is a face of codimension 1. And then I said reach, this is a face of codimension 2. Okay, in dimension 3, so the face will be the facet, and then the edge will be the reach. Because I will also talk about some higher dimensional polytopes, so it's better to introduce some terminology. Okay, so previously it was simply the polytope. Now I think I need some group. In fact, to do that, I think I'm talking about this Cox polytope. So here, this is simply the pair of the projective polytope. So I describe it in this way. So P is the intersection of this half space. Okay, it was P together with the reflections, so sigma I. Okay, so every facet there are these reflections. Okay, so okay, it's satisfying these 2 properties. So first of all, the alpha I bj and alpha j and bi, those both 0 or the both negative. Then the second one, alpha I bj, alpha j bi should be bigger than or equal to 4, or the 4 times cosine square of the pi over mij. So, okay, so the Cox polytope is the pair satisfying this property. Okay, and then I explain why I think this property is essential. Okay. Then you can easily see that when we have a Cox polytope, from this polytope, we can associate the matrix. It's very simple because we have n reflections, and each reflections we have linear functional alpha I, vector vi. So using this pair, we can cook up this n by n matrix. It's nothing really complicated. Okay. So this polytope give a matrix. Okay. Okay. So, and then I try to give some geometric meaning of these conditions. Okay. So here the two, this distinct facet, Si and Sj, okay, there are two facets. Okay. Then each facet, we have this reflection, sigma I. So Si, this facet, is correspond to this reflections sigma I. So composed of these two reflections. Then of course, this, as I said, these reflections is the codimension one hyperplane is fixed, right? So of course, these compositions act trivially on this corner. This corner of alpha I is a fixed point set of reflections, right? And then also this is the fixed point set of the another reflection, sigma j. So this intersection is codimension 2, right? But this is this compositions act trivially on this codimension 2 subspace. Okay. So these compositions induce the elements in a set V quotient by U. So this is a two-dimensional space, right? And then depends on these conditions. So if this alpha I bj, alpha j b I is bigger than 4, then it's kind of this looks like similar to the hyperbolic isometry. And equal to 4, it looks like a parabolic isometry. And equal to 4 times cosine square pi over mij looks like rotations. It's a kind of, you can guess, right? So it depends on these conditions. We have this the cases. Okay. This is okay. So then so whenever we have this this pair of adjacent facet, then there are, as I said, there are 3 cases. But when the case C, the last cases, I call this the angle. Okay, so the other 2 cases, I will say the angle 0, and then this case, I want to say the angle the pi over mij. The reason is because you imagine a Euclidean case, if the 2 reflections, and then between this angle is a theta, then the composition of the 2 reflections will be the rotations by the 2 theta, right? So here is a 2 pi over mij. So it makes sense to this dihedral angle is a pi over mij. Okay, so then from the Cox polytope, we have this matrix. So how can we have a matrix? So that this the S will be the set of facet. Okay, and then this Cox matrix Mij is simply this small Mij. Okay, and then otherwise it's infinities. So when we have a Cox polytope, from the Cox polytope, we can create Cox matrix. Cox matrix, we can have Cox group. Okay. So this I denote by WP. So the Cox polytope P will induce this group WP. Then is one of the Knight theorems by the simplex case is by Titz, and in general case by the Wimberg. This is a crucial, actually, in my lectures. So the P is Cox polytope, the setting, with a Cox group WP, okay, I already mentioned. Now you consider this gamma P, which is a group generated by this the refraction sigma I. So to define a Cox polytope, not only the polytope together with these reflections. Okay. So here this the gamma P is a group generated by these reflections. Okay. Then the Wimberg actually showed that we can think about these homomorphisms from this Cox group WP to this the SL plus minus V, and then the image, of course, the gamma P. In fact, this homomorphisms is isomorphisms. Moreover, this group gamma is a discrete subgroup of this SL plus minus V. And then I start from this polytope P. Again, you can think about, you can consider the gamma translate, so orbit of this P. Take the union. This union is always the convex set. So this is it's quite non-trivial fact. But in any case, the theorem saying that the union is the convex. And moreover, if you consider the interior of this convex set, okay, I will denote by the omega, then this group, so I will call reflection group. This reflection group gamma P act properly discontinuously on this omega P. So you have this some nice domain, okay, in projective spheres. Then this gamma P act properly discontinuously. So you can consider the quotient space, right? This quotient space will be the orbifold, which is a reflection orbifold. So that's why my title is Convex Projective Structures on the Reflection Orbifolds. And this is the way you can construct this. Here, so so in this case, I write this V. Okay, so V, it was the R to the B plus 1. Okay, so this projective sphere is a dimension D, one-dimension row, right? So in my talk I use a D. Yes, I think it's where I did here. Sorry. Okay, might be. Yes. Sometimes people use N. Okay, I use D. Sorry. Maybe it's common to use N. Sorry. Number of reflection is N. Yeah. Yeah. So here, okay. So number of reflection is N. So for example, sorry. So for example, in this, so that when the D equal to 2, if you consider the triangles, then here the N is 3. Yeah. Yeah, I mean here, yeah, polytope, yeah, that's right. So this is a intersection of the half space, but N half space. Okay. Okay. So no, it should be the N by N matrix. Because okay, so maybe I think I drew the. If you have for example, let's say the pentagon, right? Then here the N. Oh, pardon? That's right. Oh yeah, that's right. So here this Cox polytope is a pair of this projective polytope together with the reflections. Okay, but I think thank you for the asking. Okay, other questions? Yeah. So in fact, usually it's very hard to actually construct a discrete subgroup in this a special linear group, or the general linear group. But this is one of the nice way you can produce a discrete subgroup using reflections. Might be most easy way, but it's these days people use quite a lot this reflection group. Produce, for example, new Anosov representation or something new, because this is a simple but is nice to construct the examples. Some other questions? Okay. Okay, so then I think I tried to explain. I mean that this the space of convex projective structures on a reflection orbifolds, right? So if you already know the orbifolds, then it's already good. Otherwise, I using the following descriptions. So the first, you consider the face poset of this polytope is simply the poset of the face, partially ordered by inclusions. Then the two polytopes are complementarily equivalent when there is a bijection between a poset, face poset, which preserve these inclusion relations. Okay. Then of course the combinatorial polytope is simply the combinatorial equivalence class. Okay. Then now I will mention this labeled polytope. So the labeled polytope is a combinatorial polytope together with the labeling on Lich. Okay. So Lich labeling, which is function of the set of Lich to this some pi over m. So if you know the orbifold, then this is simply the reflection orbifolds. So the topologically the polytope, and then the singular locus, this orbifold is a boundary of this polytope. Okay, and then then for this facet, the stabilizer of basically this facet is G2. Okay, then also this along the Lich stabilizer should be a dihedral group. Okay. But anyhow, so this is so you can think of this labeled polytope as simply the reflection orbifolds, or as I said, it's labeled polytope. Okay, it's just polytope together with this labeling, which is the Lich labelings. Okay, because I want to fix the dihedral angles. Okay, and then talk about the space of convex project structures. Okay. Then the Cox polytope, the realizing this labeled polytope, is basically the pair of the Cox D polytopes and this the poset isomorphisms from this face poset of G to the face poset of P, such that the label of this Lich of G is a dihedral angle of the Lich of P. Then the two Cox polytopes realizing G, this labeled polytope G, are isomorphic. Then there is there's no P, SL plus minus B, such that the phi P is P prime. And then, okay, so there are this, whenever we have this, the phi, this is a SLV, and then there are this induced poset isomorphisms. Then, okay. So then I want to collect all those, the space of isomorphism class of projective Cox polytope realizing G, and then I call deformation space of the labels D polytope. So if you're familiar with the orbifolds, it's simply the deformation space of convex project structures on a reflection orbifolds. It's the same thing, but I just use a simple, the easier, terminologies, the labeled polytope and deformation space. Okay. So of course I want to parameterize this deformation space. So that's the motivations. Okay. So I want to parameterize this deformation space, but still not easy. So I will focus on some special class of the polytope, which will be some truncation polytope. Then, okay, I will explain what exactly means this irreducible. I already mentioned the irreducible large, but what exactly means these two perfect conditions. Okay, and then basically I can explain this deformation space of this object. Okay. So first of all, the truncation polytope is simply the polytope is coming from a simplex by successfully truncated vertices. Okay. So for example, the prism is a truncation polytope obtained by the truncating the simplex at a one vertex. So I just show the picture. So here this is a tetrahedrons. Okay, it's a simplex, right? 3 simplex. If you truncate this vertex, then you will get this prism, right? Then I truncate this vertex, then you will get this one. Then, for example, if you truncate this vertex, then you get this one. So the truncation polytope is simply you start from the simplex, and then you truncate successfully the vertices. Okay. So, for example, the cube is not the truncation polytope. For examples, because whenever you truncate the vertex, always you see the triangles in this case, right? So if there is no triangles, okay, this is not the truncation polytope, okay? So this is a special polytope, okay? Then the key point is this truncation polytope has a one building block, which is simplex. So basically, I will decompose such a truncation polytope into the simplices, and then I understand the deformation space of the simplices, and then we use this gluing to describe the deformation space of the truncation polytope. So that's why I can only focus on this truncation polytope. I want to describe the in general polytopes, but it's hard. So this is the special case I can deal with. Pardon? So you mean so you mean that this kind of polytope in a hyperbolic space, or? Yeah, in the hyperbolic. Okay. So when I talk about some realizing as a hyperbolic polytope, probably you need to also assign this here the angle, the labelling, right? So it depends on the labeling you put. Sometimes you can realize as a hyperbolic polytope, but sometimes you cannot. Okay. So for examples, I give it one example. It's very simple. So this is a triangular prism. Okay. So one of these truncation polytopes. Then. So as I said, it's the pi over 3. I just write it 3. So okay. So here you can put anything, but if you can see let's say the 3, 3, 3 here, okay, something like this, then probably this reminds you that Euclidean triangles. The triangles angle pi over 3, and pi over 3. So this labels of the polytope you cannot realize as a hyperbolic polytope, for example. It makes sense because it has this Euclidean triangles, basically. Yeah. So it depends on but if you change some of the labels, and then if you put some labels, it's a nice way, then you can actually put inside hyperbolic space, 3 space in this case. So it depends on okay. Okay, so previously I think I talked about when you start from the Cox polytopes, you can produce the Cox group. Similarly, when we have a labeled polytope, we can produce the Cox group, right? Because let's say if this is a labels polytopes, then we have, this is a triangular prism, so it has a 5 facet, okay? Then because let's say this one, the first facet, and this is second facet, this is a 3. Okay. So 1, 2, and between this is diagonal angle is pi over 3. So we can produce the Cox matrix similarly as Cox polytopes. Then from there we can have this Cox group. So then I call Label's polytope G is, for example, irreducibles when the group is irreducibles. Okay, because for example, I already explained Cox group is when the Cox group is reducible. For example, Cox group is spherical, Cox group is affine, but corresponding the polytope I call also the irreducible, spherical, affine, and etc. Okay. Then look at the link or the vertex of this polytope, and then this is simply the link of this underlying combinatorial polytope with, the obvious Ricci labellings. So, for example, here's 2, let's say the 3, let's say the 2, this, and then this one. What will be the link of this vertex? The link is the triangles, right? The link of this vertex is triangles, right? Then the H labellings, in this case, Ricci labelling is 2, 3, 3. Okay, so then the Label's polytope is we call the perfect if the link is a sphericals, and the Label's polytope is a 2 perfect, then the link is perfect. Okay? So if you for you it's a little complicated. And the perfect means, in fact, the reflection orbifold is a closed orbifolds. Okay. 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 So then this is one of the main theorems. Okay. Okay. So I should mention that this joint work is the Su-Young Choi and Ludovic Marquis. So when the G is these conditions, when the deformation space is non-empty, then in fact, this dimension D has an upper bound, which is 9. Moreover, this deformation space is a union of open cell of the dimension something, but this something, here the E plus minus D, here the E plus is simply the number of Ricci with the label different from the pi over 2. Okay, so if you simply count, so for example, if I put here 2, 2, 2, okay, so then so how many here? So number of Ricci with a label different from the right angle. So here, the 3 is different from the right angle, right? 3 and 3 and 4, right? So there are 4 of them. Okay. So this guy has the union of the finitely many open cell of the dimension 1. One-dimensional deformation space. Then, if there is a hyperbolic Cox polytope, realizing this labeled polytope G, if and only if, in fact, this deformation space is connected. Okay. And then I try to give us some remark. In fact, this number of connected components can be explicitly computed. Okay. So probably I think if I have time, then I explain how to compute. Then this labeled polytope is not truncation polytope. So as I said, truncation polytope is one of the simple class of the polytope. But if not such a cases, then in fact deformation space can have some topology. Meaning that, for example, so may not be the union of open cell. For example, there is the perfect labeled 4 polytope such that this deformation space communal to circle. or it can be homomorphic to this kind of space. It's like X, right? Shape. So my point is, so the labeled polytope or reflection orbifold is this kind of truncation polytope. Then the deformation space is a union of open cell. But in general, it might be more complicated. It can be a circles, deformation space will be the circles, or deformation space homomorphic to this kind of X shape, for example. Okay, so that is a main result. And then now I try to explain how you can actually prove such a theorems. So I try to give us some kind of the idea of the proof, okay? The main idea is that, as you already noticed, that when you have a Cox polytope, from the Cox polytope, you can produce the matrix, okay? So that kind of matrix I will call the Qatar matrix. So all the diagonal entry is 2, and then the off diagonal is less than or equal to 0. Then, for example, Aij is equal to 0, then Aji equal to 0. And then Aij, Aji is bigger than or equal to 4, or 4 times cosine square parabol. So exactly the conditions for this Cox group, Cox polytope, okay? But this here, there is no this reflection group involved. It's simply the matrix, right? It's a m by m matrix, okay? It's a matrix. And I mean, such a matrix is reducible if in the reordering the indices, you can make this kind of like a decomposition like A1 to A2, but otherwise I call the irreducibles. Okay. Then the irreducible, actually the Qatar matrix has a simple eigenvalue, which actually correspond to the eigenvector with positive entries by this Heron-Frobenius theorems. And then when this eigenvalue is positive, then I call this matrix is positive type, 0 then 0 type, and negative and then negative type. Okay, let's look at this simple Qatar matrix A. When, let's say, this value is a -2, then in fact, this is a 0 type. In fact, this eigenvector will be the 1, 1 eigenvector. 1, 1, right? This is eigenvectors, and then eigenvalue is 0. Right? Corresponding eigenvalue is 0. Okay, and then okay, mu is less than 2, then it's negative type. And so here, in fact, so this case, so let's say this is a 1, and this is the second in the reflections. From here, you consider this 2 by 2 Qatar matrix. It's the ideal case, exactly happens mu equal to -2. And then if you deform it, then it's become hyper-ideal. Then exactly happens when the mu is less than -2. Okay, so then, previously I think I mentioned when we have a Cox polytopes, then we have a Qatar matrix, okay? But there are some ambiguity. So here the reflections, so it gives us this linear function alpha I and vector vi, right? But this pair of this linear functional and vector is up to the simple actions by this positive real numbers. Okay, so lambda I, you multiply here lambda I, and then the other one is 1 over lambda I, then it still gives us same reflections. Right? It's clear. So the Qatar matrix is not really just defined by this Cox polytopes. Instead, there is equivalence relations. It's simply the two Qatar matrix equivalence when there exists a positive diagonal matrix D, such that this one Qatar matrix A prime is a D inverse. Okay. So we can talk about equivalence class of Qatar matrix. Then in fact, this is a well-defined. So Cox polytope give us an equivalence class of the Qatar matrix. Okay, so I already mentioned this one. Then this is a crucial theorems by the Wimberg. So A is Qatar matrix. Then assume that A is irreducible and negative type, and the rank D+1. Then there is unique Cox polytope, the D-dimensional polytope. So here the rank is D+1. So we have a D polytope, unique up to this SL plus minus, such that the Qatar matrix of this Cox polytope P is exactly the same thing as A. So previously, I mentioned that when we have a Cox polytope, then we produce a Qatar matrix, but these theorems tell us the opposite directions. So given Qatar matrix, you can find unique Cox polytope P. So the point is, to understand the space of this Cox polytope, you just try to understand space of the matrices, Qatar matrix. It's way simpler, right? Especially when the polytope is a simplex, it's even more simple. Okay. So this is one of the key ingredients. So instead of looking at the Cox polytope, now you look at the space of the Qatar matrices. So, so now we need to understand Qatar matrix. And there are some more ingredients. So here, so G is labeled polytope with this Cox group W, and the P is Cox polytope realize this labeled polytope, with the Qatar matrix A. Then you consider the K2 pool of the distinct elements, let's say the K circuit. Then this circuit, K circuit, we define the number simply the multiplication of this the Qatar at the entry of the Qatar matrix, the A I1 I2, A I2 I3, and A I K I1. But you can easily notice that this number does not change on this choice of the representative or this class, because here there are this I1, but here there again I1, but it's a second entry, right? Here the I2 is the second entry, but here I2 is the first entry. So there are this, the real number lambda I, but it's the cancel out. So the point is that this does not really depend on this representative. Okay? And such a number is called the cyclic product. Then the Wimberg actually shows that, in fact, the Cox polytope P and P prime are isomorphic if and only if Qatar matrix AP and AP prime are equivalent, or all the cyclic products are equal. So basically, it tells us that the cyclic products will be the parameters. Because I want to parameterize the space of the equivalence class of the Qatar matrices, but this equivalence class is determined by cyclic product. So if you understand this, basically the space of these cyclic products, then that's it. Okay. So now I think I want to use this cyclic product. Okay. So this is one truncation polytope. Okay. And then I split them because reason is, if you remember the hyperbolic polygon, and then I split to the two triangles. Okay. This guy is one truncation polytope. I split to the two simple polytope. In fact, this guy is basically the tetrahedrons. This guy is basically what sense? This guy is a, yeah, I think it's, I have 5 minutes, okay. So, okay, for example, this guy, okay, so this is the tetrahedrons, right? And then if I truncate only these 2 vertex, then you get this one. So that's why what I'm saying that this is basically the so I call the once truncated simplex. The simplex, I just choose some of the vertices and then truncate it once. That's it. It's not allowed to truncate, keep going, okay? Just once truncated. So this is one building block, and this is one building block, but this building block is basically the simplex. Because as I said, once truncated. So if I parameterize this guy, then gluing, it will give you the description of the deformation space. Okay. Okay. So might be, I think might be just go a little bit further. So, so as I said, now I want to understand, in fact, the simplex, okay, simplex case. But then there are this lemma. The labeled simplex is a perfect case. In other words, it's a closed the reflection of Orbifolds whose underlying space is a simplex. Okay. In this case, is irreducible large if and only if the group is a Lanner Cox group. So what is Lanner? Is the Cox group is large, and if you remove just one generators, so this WS minus S, so this is a sphericals. Okay, maybe I think 2 runners. Then, in fact, for the Lanner or the 2 runner Cox group, there are this classification is already known, and then there are this upper bound for the dimension. Okay. So that's why the dimensions has this upper bound. Then, as I said, this lemma exactly the descriptions for the deformation space of the labeled simplex. Okay. So in this case, there are this is basically the Cox diagram, and then depends on the diagram, we can easily see that this deformation space for the simplex, the labeled simplex, is open cell. That you can do is a simplex. You can do. And then, for example, this is one example how we can do. So you can see here the cyclic products, right? Then you can easily see that. So I mean, the log of this guy plus log of this guy plus log of this guy is 0. So it has a okay. So previously I explained the cyclic products, this guy. But this, whenever you determine this guy, then this cyclic product also determines, because for example, A25 times A52 is already fixed number, 4 times cosine square pi or something, right? So one cyclic product is determined, then the other one. So so ratio is determined, then the cyclic product is also determined. Okay, but in any case, you can see that there are 3 variables, but 3 variables has 1 relations. So in this case, it has a 2 parameter space. So my point is that the deformation space of the labeled simplex, you can easily describe using Kata matrices or the cyclic products. Okay. So then I think I need to. Then I think I should explain some these truncation operations, because as I explained before, some triangles, and then I deform it, and then there are some truncations, right? So you can do similarly this kind of the simplex, you deform it, and then there are some truncations. Okay. Yeah. So then here, so this is a 3. So maybe I just explained this one, then I stop. So here the 3, 3, 3. So this vertex. So if you imagine, in fact, this guy, you can realize in hyperbolic 3 space. And this vertex is ideal vertex. And then if you imagine the hyperbolic space, and then the link of this vertex, you can see the Euclidean triangle, pi over 3, pi over 3, pi over 3, Euclidean triangles. But then, of course, in hyperbolic setting, you cannot deform it. But in this projective setting, you can deform so that you can actually truncate this vertex. And then in a polygon, if you deform it in a hyperbolic setting, then there are the length of edge. Okay? Similarly, there are some corresponding. So the length might be can be generalized. In this case, the log might be just ratio of the cyclic product. Okay. So because when in this kind of situation, so this ratio of the log is 0, then you cannot truncate the vertex. When this is different from 0, then you can truncate. And then whenever this number match, you can actually glue. And then, in fact, in the projective setting, there are some more some deformations, like some bending deformations. But using those, you can actually the parameterize whole space. But I think it's right. I should stop here. So then, thank you.
So, any question? So, you can have some idea about the space of deformation here?
Yes. So, so yeah, exactly. So I explained how to, describe this the special case of this reflection orbifolds. So maybe I think using a the description of this representation space. So the space I describe is basically the home. Okay, so might be the subspace of this home. The representation of space of this WS. So this will be the fundamental orbifold fundamental group of the reflection orbifolds to the Lie group SL plus minus T plus 1R, where there exists this omega. Okay, well, this omega of course depends on the representation rho. Okay. This is properly convex. Of course. This is a SD. So it's actually the dimension D. So yeah, it's D. Properly convex, and such that the quotients by the rho WS. Okay, so this is isomorphic to this orbifolds. So that might be, I think, as I said, this will be the pi 1 of the orbifold fundamental group of the reflection orbifolds O. So this is a relate. So this is a relate to this O relate to this. Might be, I think I just write because previously. So this is a Label's polito. The same thing as the orbifold, reflection orbifolds. And then this is and then the quotient by, okay, this is G. So yeah, the space I parameterize exactly this space. Then I give some more commentary way to explain. But
Okay, so if there is no further question, let's thank Gye-Seon for this wonderful talk. Thank you very much.